When we add and subtract with significant figures, we need to keep as many digits after a decimal point as there are fewest digits after a decimal point in any of our measured values. The easiest way to keep track of this is to line up decimal points just like we're in elementary level mathematics when we add and subtract measured quantities. So in every problem that we perform an addition or subtraction step for with measured values, we're going to align decimal points. In part A, notice that an implied decimal point is aligned with 17 and the measured quantity 0.000000313. When I add these two quantities together, I'll add them like I normally do. I'll keep all of the requisite zeros, 313, and a 17 with a decimal point right at that cutoff. The important part about this cutoff is that everything that's to the left of this cutoff, this way, is significant, and everything to the right of that cutoff is not significant. We really don't care about those numbers. The only thing that we'll use them to infer is whether our last significant digit rounds up or stays the same. If the first non-significant digit is 0 all the way up to 4, we'll keep our final significant digit the same. If our first non-significant digit is 5 or greater, then we'll round our last significant digit up. In this case, the first non-significant digit is 0. The last significant digit stays the same. Everything to the left of this cutoff is significant. We have not rounded anything, so our final answer we'd report for this problem, part A, is 17. In part B, we also have decimal points aligned. Here, I'm going to draw a cutoff after the measured value with fewest digits past its decimal point. That's at the 1 after 3.1. I'll still subtract like I normally would, except this time I'll have 2 digits with a decimal point to the left of my cutoff. Everything to the left of this cutoff, again, is significant. Everything to the right is not significant. We'll use our final significant digits rightmost non-significant digit to inform rounding. Here, our first non-significant digit is a 6. That means that we round our last significant digit upwards. Our final answer is 1.9. In the next problem, we add 0.000343 and 0.17. Here, I'll draw the cutoff right there after the digit that's got fewest places past the decimal point. We'll add like we normally would. Everything to the left of this dividing line is significant. Everything to the right is not significant. And we'll use our first non-significant digit to inform whether we round up that last significant one. In this case, our first non-significant digit is a 0. That means the 7 before it doesn't round at all. Our final answer here is 0.17. In the next problem, our cutoff is right at the decimal point because there are no decimal digits after 78. In this case, again, we'll round like we normally would. After we have subtracted, a calculated result for our subtraction shows a 77.01. Our first non-significant digit is a 0. That means that we do not round our last significant digit, the 7. We keep it intact and report our final answer as 77. When we're given a problem in which we don't have decimal points aligned, it can be helpful to line them up. In part E, we might rewrite that problem as follows. 336,000 minus 33,000.03. In this problem, we have, again, no decimal point after our topmost measured quantity, only at the bottom. Here, we'll add and subtract like we normally do. This time, we'll end up with this quantity 302,999.97. We've got to figure out whether this first non-significant digit rounds our last significant digit up or keeps it the same. In this case, this is greater than 5, meaning that it will round the next digit before it up 1. Well, we can't round that digit up 1 without rounding the digit before it up 1. So this sets off a chain event where we have to round that one up 1. And we can't, well, round that 9 up 1 without rounding that one up 1. And we can't round that one without rounding this one. And finally, we can stop. 302,999.97 rounded up is 303,000. That's the answer to this problem. In the final subtraction problem, we have 0.99 minus 0.1. Here, again, if we align decimal points as proper, we'll have a calculator result that shows us 0.89 with significant digits on the left, non-significant digits on the right. Our first non-significant digit forces our last significant digit to round up, giving us a result of 0.9. To practice with all of the information we've learned so far, let's work the rest of these problems quickly. In the first set, we're going to think about how many significant digits there are in each of the following measured values. In 87, there are 2 significant digits, 1, 2. In 190, there are 3, 1, 2, 3. In 0.000190, there are 3. In 606.0, there are 4. And in 1.008, there are 4. To round values to a certain number of significant digits, like 2 sig figs, we've learned to count off. Here, 1, 2, and a round means that this number, 86,730, rounds to 87,000. This quantity, rounded to 2 significant digits, must have just this number and this number. To keep 2 significant digits and an order of magnitude intact, we maintain a 0 without a decimal point, 120. To keep 2 significant digits here, we count off our first 2. This 5 rounds the 4 before it up, and we're left with 0.00035. In this example, 2 significant digits here, a 5 rounds the 5 before it up, we're left with 0.056. And lastly, 2 significant digits, a 9 rounds an 8 up, so we're left with 9.9 million, or 9.9 times 10 to the 6th if you prefer. To determine the number of significant figures that are in a final answer after a computation that involves multiplication and division, we count total number of sig figs. In addition and subtraction, we count the number of significant digits past a decimal point and use the thing with fewest sig figs past the decimal to inform where a cutoff is. If we multiply 0.2, which just contains 1 sig fig, by 43.98, which contains 4, our final answer can only have 1 sig fig. If we multiply 43 million, which has just 2 sig figs, by 0.00546, which has 3, our final answer can only contain 2 sig figs. If we subtract 17 from 43.0, we'll only be able to keep 1 digit past a decimal. Everything to the left of that first decimal digit is significant. In total, this will yield 3 sig figs at the end. If we subtract 3.0 from 0.00235, again we can only keep from 1 digit past the decimal point left. That's going to result in just 2 significant digits available for us in our subtraction. Subtracting from 143.000, 3.45, once more we think about the quantity with fewest digits past its decimal point. It's the second quantity here. In this case, we'll be able to keep 2 digits past a decimal point, plus this one, and this one, all the way out to the hundreds place. That's a total of 1, 2, 3, 4, 5 digits that we'll be able to keep. In 3.40, which has 3 sig figs, times 0.04, which just has 1, we'll only be able to keep 1 sig fig at the end. Mixing and matching operations, where we multiply and divide. Here are 3 sig figs, here are 3 sig figs, here are 4. Our final answer can only have 3 sig figs in it. Here are 4 sig figs, 4 sig figs, and just 1. Our final answer can only have 1 in it. Lastly, here are 3 sig figs, 1, 2, 3, 4, 5, and 1, 2, 3. 3 sig figs can go in this final answer. When we add and subtract with sig figs, we draw a line of demarcation. Everything to the left is significant, everything to the right is not. We won't have any rounding up. The answer to part A is 4. When we multiply and divide, we count up total sig figs. 3, 3, 3, 4, 2, 2. Our final result can only have 2 in it. When we punch this whole operation into a calculator, and be careful here to put everything in the denominator in parentheses to ensure that you're following order of operation in the calculator properly, and round to 2 significant digits at the end, we end up with 1.2 times 10 to the 3. When we add and subtract, here, this is a little bit offset. We have 0 there, so we'll have 0, 3. Only digits to the left of this line of demarcation will be significant. So we'll have this guy 5, 5, 8, 8, 3, 3, 10. This is our answer. Subtracting these two quantities from each other, again, only things to the left of this arrow are significant. In this case, we will not be able to round up once more. So our final answer here ends up as 58. Draw a line here. Again, only things to the left of our line are significant. Add and subtract like normal, but again, we don't have to worry about rounding. 6.0 is our answer for this question. Align everything here, and we'll find that since every quantity has just 1 digit past a decimal point, our final answer should be reported to the tenths. And when we plug this into our calculator, we get 9.5. Counting significant digits in scientific notation quantities is as simple as just looking at the number that's multiplied by a base 10. Here, all we have to concern ourselves with in part A is the 3 and the 0 for 2 significant digits. This whole thing we can ignore. In a decimal point measured quantity, we count from the left, start counting on a non-zero, and count our way all the way to the end once we begin. 2 significant digits. Scientific notation, again, all I look for is a number out in front that has 3 significant figures. Here, no decimal point, therefore I start from the right and only begin counting on my first non-zero. There's only 1 significant digit here. The placement of a decimal point, however, changes so that I count from the left. And this quantity now has 6 significant figures. Again, I don't care about the base 10 in scientific notation for the purpose of counting sig figs, so here I'm just going to look at 5 total significant digits.